Welcome to the BE seminar series. It's my distinct pleasure and privilege to introduce Dr. Dongfang Wang. He's a professor in the Department of Surgery at the University of Kentucky, and he's also the president of WZ Biotech. He graduated from Hubei College in China, and he was a practicing cardiovascular surgeon. And today he's here to talk about some of his numerous inventions, and he has his own company as well. So without much further ado,
Thank you. Thank you, Guru, for your invitation. As Guru introduced, I was a cardiac surgeon, so that make my research a little bit different. And my first research did not have fancy technology. We focus on patient need. So we use the simplest technology to solve the problem. We have a lot of conflict of interest of all my presentation will be our own research and some of the commercial, some of the on the technical technique. I worked with Swiss for 17 years since I relocated from China. We work together. We work on the Schreiner grant support for many, many years. We got a lot of financial support from them. In our path, we come here. The first, we work on F-core and the total artificial lung, and then eventually we find those things looks fancy. Research is very sound, but may not apply to the patient immediately, and it's a long way to develop it. When I come here first, I switch. They are doing F-core Arterio-Venous CO2 removal. Because of CO2 will accumulate if you have acute chronic lung diseases. It's very hard to remove. And then they use arterial and venous shunt and have about 1 liter blood go through a gas exchanger and then have sweat gas. You can remove a lot of CO2. When Swiss go to the Germany, present our technology, there's a company adapt our concept, and then they commercialize it to the patient. They have done a lot of patients before our Lumen Cannula came out. It looks like it's fancy, simple, looks like we do not need a pump. However, they still have some problem. The first thing is they do not have oxygen transfer. There's a lot of patients that still have problem of hypoxia. You cannot solve this problem. The second thing is they claim have total CO2 removal. However, those data was collected in a completely sedated sheet. If it's a normal patient not sedated very well, they do not have the capacity to remove CO2. There is no company that this is true. However, using the major arterial cannulation, that could cause a serious problem. They do have problem in the patient side and the cause amputation because of that. And it's not ambulatory. And then, therefore, we realize we need oxygen for the patient as well, not only the CO2. And then the next year, we have a project. We have a paracorporeal total artificial lung. What we do is PA to PA. We have anastomosis. Here is the heart. This is the PA. And then we have the inlet graft go to the artificial lung, and then oxygenate go back to the PA. And then we have snare here. They disconnected blood flow. And then the blood goes through the LVAD, go to the artificial lung, and then back to the pulmonary artery. Therefore, the whole cardiac output blood, venous blood goes through artificial lung, fully oxygenate, remove CO2, go back to the native lung. Our animal experiment, the result is very exciting. However, more personally, I think there's a lot of problems. Who need a total artificial lung? The patient need a total artificial lung is the patient usually is terminal chronic lung diseases. Those patients mostly they have RV function compromised, and then you insert additional artificial lung, mostly have lung graft, and we worry about those patients' right heart cannot power blood, total blood flow goes through artificial lung, and then goes through relative circulation, pulmonary circulation. And the artificial lung we have serious thrombosis. And then we try to, we decided to go somewhere else to help artificial lung. And then we think this is the answer for the patient. One cannulation, and then go a pump, and then go artificial lung, so the patient can carry out and move around. From previous slides, we see the artificial lung. If you work a long time, they have significant thrombosis. And this is the electronic affinity. Every time when we go to more than 1 week, they have significant thrombosis. And then we have a pattern, we're trying to solve those problems. We have even blood distribution. Here we have blood buffer, so the total artificial lung inside we have very even blood flow. They integrate and the pump there inside, and then we can pump. This is pneumatic driven pump, and have even flow inside the water buffer. Then here there is a flow distributor to achieve even blood flow. We realize the problem here in current technology. Everybody talk about artificial lung, everybody talk about pump, and actually they just like you guys make a tremendous progress in blood pump and other people do artificial lung. However, how to hook up those devices to the patient? That is the people have not paid attention for very long time. So no matter how great of your device and how do you hook up, get the device connected to the patient. And the same thing happened to the ECMO. ECMO has been invented from just cardiopulmonary bypass simplified through there. And 50 years, there's no change until year 2009. And then we think in 2004, we think about if you try to achieve total oxygenation and the total CO2 removal, you need 3 cannulation for VV-ECMO. Because if you have the cannula in SVC, which is severe venous animal, for withdraw blood and infuse the oxygenated blood to IVC, and then you have problem to take the IVC blood out. And if you want to do so, you need 3 cannulation to achieve total blood oxygenation and CO2 removal. And then we think about if we can do something, have just 1 cannulation to solve this problem. Dr. Schwitzenberger in 1989, they worked with industry to come up with single cannula, double lumen, to do the VV-ECMO to try to achieve total oxygenation, total CO2 removal. However, this device only work in the baby. Because you all engineer, the first thing, the problem is they cannot withdraw blood from the lower body. And then the deoxygenated blood come out and mix with oxygenated blood will compromise and cause the recirculation. And then the oxygenated blood will take out again. Recirculation is not efficient. The most difficult, even though this cannula is very good, very convenient, but the most difficult problem is you cannot make it bigger. If you make it bigger, here you know the physics. If you make it bigger, because they use a septum here, and then you have infusion lumen, it will be very high positive pressure, and then you have drainage lumen, it will have very negative pressure. Think about the scenario, if you want to increase blood flow because the patient needs more oxygen, more CO2 removal, and then you have more positive pressure, more negative pressure, they shift. This septum will shift. And then actually the real scenario that happens, will be this septum will shift, decrease blood flow, it won't work. So you cannot make it bigger for adult usage. And then we come up with the idea of have our own Lumen Cannula. We have a patent file 2004. And we have the infusion lumen around side because my physics teacher from high school, they teach me the round shape is the most stable geometry shape. And then we have very thin wall, round shaped infusion lumen. And then we have reinforced, very thin wall, reinforced membrane. And all of those made in polyurethane deepen technology. Actually, those technologies very simple, but it's very troublesome. It's not easy to do it. And we work with Avalon company, a lab company in California. We sell the patent to them, and then they develop these cannulas. The good thing of this cannula is not like the old cannula. We can withdraw blood from SVC. We can withdraw blood from IVC. Therefore, we have the potential to have the total venous blood go up, and then have the infusion toward the tricuspid valve. This design became very successful, and on the market in 2009. This device is not only achieve the total gas exchange, and make the ambulation possible because you see this sheet, and they just have one side cannulation, have a pump, and have oxygenator. And this sheep, we cannot put the sheep on any sedation and awake. They can eat normally, and this will cause a complete story and very helpful for the patient recovery. And this device that has been used in the patient and enable patient to walk around, which is very important for patient recovery. Now this is a standard. This is a standard for the patient reach to the lung transplant. AATS, American Association of Thoracic Surgery. They put into the protocol, and those patients reach the lung transplant could use this technology, this cannula, VV-ECMO ambulation to promote the recovery of the diseases from chronic hypoxia and high CO2. This has been used at Columbia University, very early stage, and Pittsburgh as well. It's widely accepted around the world. There is another things. When the patient have a cardiogenic shock, of course, LVAD is very good. However, if you use LVAD, you need open chest, right? And it's traumatic surgery. Sometimes the patient's situation is not good. It's not convenient. And then you use VA-ECMO. But the VA-ECMO have a problem. VA-ECMO, and then venous blood out, arterial blood in. However, venous catheter cannot take all the venous blood out. And then there is pulmonary circulation area place. They got venous blood directly go to the pulmonary artery. And then the blood, the unoxygenated blood, go to the LV. This blood in LV do not have oxygen. And then the pump out, what happened? They supply the heart. And then the heart is supplied by the blood, virtually is venous blood. And this venous blood also supplied to the head. This is why there is a lot of patients, they have VA-ECMO. And then they have everything's right, but the clinical outcome is not good. We call this differential hypoxia. To solve this problem, we propose to use our double Lumen cannula, and see here, withdraw the blood from SVC and IVC and oxygenate, and then go to the arterial system, supply the blood for lower body. And then you have another branch, have the oxygenated blood, go there, infuse to the right heart, and then this go to the pulmonary circulation. And then you increase the oxygen level in the LV. And then the heart, native heart, and the brain do not have oxygen supply. And we tested this in an animal experiment. We have a respiratory failure animal model. You can see here the oxygenation in the abdomen aorta is very, very high. However, the situation here in the LV is very low. The PO2 is very low. That is why the patient's heart have the venous blood to supply. We do experiment and different kind of VV flow, and then the 10% make difference, raise LV saturation, and then 50% significantly raised, and 30% they can increase the saturation to 88%, which is good enough for patient. This paper published recently. We still have problem. We solve this problem, and then what if the patient have combined right heart and lung failure? VV-ECMO did not solve the problem. And then we introduce the concept of Axial LVAD. We do the experiment all the way back to 2007, 2006. We use actually is LVAD and plus oxygenator. This is our experiment with the sheep. And here is a pump, is a debated pump, and then here is oxygenator. And then they got blood back, the blood from RA and back to the PA. Therefore, the oxygenated blood go to the PA, and then you unload the RV. The patient RV got support, and then oxygenation solve the problem. So Dr. Hoops from UCSF, they take this technology, take this concept, and apply in the patient, and it was used nationwide and internationally of this concept. The LVAD have their problem. The problem is they are too invasive. You still need to open the chest, just like LVAD. And you need a major cannulation, and you need to open the chest again and take it out. We developed another, we think about another technology based on our previous patent. Have percutaneous. It could be just the LVAD, or it could be Oxy-LVAD, so percutaneous. You can have optional oxygenator. You withdraw the blood from here, from LA, and go out, pump, oxygenator, and then go back to the PA. We got the financial support from NIH, and we have a prototype under their support, and tested in animal, and it works very well. However, there is a company, we are very happy actually. They take this concept, and then they have their product, and then they use off-label application used in the patient. We're still very happy. They can do that, some patient benefit from this concept. And now Fontan. I know University of Louisville are very good at Fontan. They have financial support from NIH. The Fontan circulation, the characteristic is they do not have this part. And then they have TCPC, guided blood from venous system directly go to the LV. So you do not have the RV, LV have to pump the systemic circulation and the pulmonary circulation in serials, and then eventually all of the Fontan circulation will fail. It's not, currently the outcome is very good, but 10 years later they have mortality. 40 years later, mortality is way much higher, it's very high. And 50 years later, and the majority of them may fail. People may think 40 years later, and then the patient is good enough, and then they already survive 40 years. However, you think about the patient that finished the Fontan, is a teenager, under the teenager is about 10 years old. And 40 years later, this patient is just 50 years old, mid-age. And then they failed. What can you do with that? The only option is heart lung transplantation. The heart lung transplantation, you know, as long as the Fontan circulation fails, it goes worse and worse, very quick, and die. and then the Fontan assist is really required. And we have the we want to develop a Fontan assisted device to increase the pulmonary blood flow, to withdraw the blood from the SVC and IVC, pump to the RTA and the LPA, which is very challenging because you have two inlet system. It is a control direction from SVC and IVC, and you pump to perpendicularly to both branch from RTA and LPA. And the currently existing technology is very, very hard to adapt this spatial anatomy. And the people and all of the scientists have spent a lot of effort trying to use currently existing technology to assist the fading Fontan circulation. Some pump is even very small, and they even catheter pump. Unfortunately, it's very hard to work. The first thing, the traditional centrifugal pump, or pneumatic driven pump, if you're trying to use this technology to assist the fading Fontan circulation, you have to complete this is a fountain. You have to completely take down the fountain. And then to elastomos SVC, IVC again, to generate compliance chamber, and then allow to the inlet cannula pump, take the blood from SVC and IVC, and then get this blood flow back to the PA, and then you have to connect the both sides of the PA together for infusion. That surgery is even more complicated than Fontan itself. And very, very few people do this kind of surgery. And then this is your partner, Rotary. They open a new area of Fontan assist. They have two catheter pump, hemo pump, to assist to supply total Fontan circulation, which he published. And then this is the first assist. And a lot of people trying to use Impeller catheter pump to assist the fading Fontan circulation. They always have problem. Either you need to modify the Fontan circulation, open the chest, have some snell to prevent the recirculation, or you can just assist one side. All have different kind of problem for real application. And this is Dr. Martin, and they have a very, very nice pump here and here. It works very well. However, if you're trying to assist from SVC and IVC, you need a two pump separately. It may work. And this is your partner. This is a very genius design. They can withdraw the blood from SVC and IVC and then go through both RTA and LPA. This is very, very good genius device. The problem is, a little bit I concern is challenging to have the pump stay here. Because you have catheter, it's go out of the body. And the patient, any kind of movement, even sedated patient, you do daily nursing. You may move the patient. This may not align very well and may do not work very well. Those problems maybe you can fix them somehow. And we still go to very rude technology, very simple technology. We still use our cannula. Same thing, this is our Lumen Cannula, previous Avalon Lumen Cannula. You can withdraw blood from IVC, SVC, and perfuse to the pulmonary circulation. This is the first feasibility study we published in the Thoracic Surgery. And we have developed a Fontan sheep model, which is extremely hard. My surgical experience really, really heavy. And this sheep model, we do not use cardiopulmonary bypass machine. We just we made our cannula from a company to have a temporary bridge. And then we have like ECC, extracardiac conduit, anastomosis to SVC and IVC, and I have a lot of anastomosis. We do this anastomosis first. side to side to RTA. Therefore, the blood from SVC and IVC flows through this conduit and then go to both sides of pulmonary artery. The problem is, this is a large sheep. It's not the baby. They have complicated congenital heart diseases. In real clinical scenario, you do the Fontan surgery procedure by 2 stages. You do hemi-Fontan first for SVC, and then you have completed the total Fontan later, about 3 or 4 or 5 years later. And then you try to do 1 stage. When you finish this, the sheep will express as a fading Fontan circulation. This is perfect for our purpose. And we tested this in animal. This is our real animal. And then we first thing we have to prevent the recirculation from here to here, here to here. We have a valve on the conduit. We have a valve here and we have a valve here. A lot of blood flows through here to the central, through upper to the central. And then we do, this is our animal. And we achieved total Fontan assist performance. This is our result. When you finish animal mode, this is fading Fontan circulation. It's characterized by very high CVP and very low blood pressure, because this is heart failure. And the lactus, when you finish the baseline is good. When you finish TCPC and the increase, and the after assist, and the recover, this works very, very good. They have some problem because you have to change the way the doctor's performance. Every time you have to ask a doctor to have a valve inside, and the valve may add additional resistance to the patient, and then this system is very low pressure. Any increase of resistance will cause fading Fontan circulation exacerbate. And then we have the umbrella here and here between the inlet of IVC and the outlet of the total pump, the total perfusion. The same thing here. We have umbrella here and here to prevent the recirculation. And then they have the blood pump through from IVC and SVC, and they take out the pump and perfuse to the middle. All of this perfused blood will go to the pulmonary circulation. They do not go back to SVC and IVC. And this thing is safe. Any kind of assisted device you have opportunity, your device will fail. If your device will fail, there's especially in this one specific one, you will have additional resistance. The patient may die immediately because there is no blood goes through SVC, IVC, and then go to the pulmonary circulation. And then the cardiac output will be very, very small, very, very low. The patient will die immediately. And this simple design is this one-way valve umbrella can collapse, allow the fading Fontan circulation blood through the original blood path go to the pulmonary circulation. And this is our first preliminary prototype. And we made there in our lab and our company. We tested in the fading Fontan circulation sheep, and we have very good performance. You see here the fading Fontan circulation, and then when we run this system, all the hemodynamic restore. And then if you stop, clamp the pump, they get fading Fontan circulation again. And then when you restore, they can assist about 60 minutes. The good thing of our animal model, the very good thing is this animal model, we do not have blood transfusion. Blood transfusion in sheep, in our experience, is a disaster. We have tried twice. All the sheep have the problem die of blood transfusion. In this animal model, we do not need blood transfusion. And then at the end of the experiment, the blood hemoglobin is still keeping normal range. This one is just simply modified from our AvalonElite Cannula. And we you have stagnant flow here, and here is okay, basically it's here. And then we see the thrombosis. And then we have outlet here and outlet here. And then the blood wash on the umbrella, and on the umbrella go to central, and then eliminate thrombosis. Stagnant flow increase the thrombosis. This is our prototype simulation. This is cannula, not last very long. If you go through the pump, in the cross section there, there is no place in fading Fontan circulation to accommodate any pump inside this place. It's very, very limited space. And then we trying to do something like axial-centrifugal flow pump for fit in the Fontan circulation inside the venous, vena cava. Vena cava, especially in Fontan circulation patient, they have higher IVC. Therefore, the vena cava is very, very, very big. Allow us to design the pump inside. This actually is very, very simple. The principle is very, very simple. And then we have a motor here. We have a bearing here, and then bearing here. We have screw. This is axial screw here. And then here we have a segment. We have a long segment. Why we have a long segment? Because we have to allow this catheter pump move up and down. As long as this segment inside RTA and LPA, they do not compromise the performance. This is beauty. And then the axial flow generated from here and here. When you pump, runs very fast. So any kind of axial flow pump, heart molecule, anything. When you run very fast, they generate a centrifugal force very, very significantly. And then they will pump from here and here. Since the delta P in fading Fontan circulation is very, very small, maybe 10 centimeter water, 10 millimeter mercury make a tremendous difference. So you do not need run very fast to generate this pressure, delta P. This is our pattern. This is our 3D file here, and this is our simulation. Because we are very busy, we are a very small group. Virtually, we have very few people. Not as lecturers, and you guys have so many people work together. We have not started this project yet. We only do the CFD. You can see this is performance. You can see even 600 can generate 5 liter blood flow against 5 millimeter mercury. And if you go 900, this is more than enough for most of the patients. So you do not need to run very, very, very high. They can perform like to assist the fading Fontan circulation. And the second thing is, recently we collaborated with Dr. Guru and this group about the new SBR grant, and we find out we're trying to use temporary LVAD to assist LV failure. However, it's very hard. You have to open the chest, and then you have to do, while open the chest, have 2 access. One is from apex, or another one from SNE and Aorta. We're still trying to use cannula to solve this problem, especially this problem is very serious in neonatal. We presented this result in ATS the year before. Currently for neonatal, especially for neonatal pediatric LV support assist, most of them use VV-ECMO. VV-ECMO is very common to use. They have a very complicated circuit, and with anticoagulation level relatively high. Most of the time, they do not completely fully unload the LV. And the LVAD, and they are better because they have low level of anticoagulation. And the burning heart is core is the only FDA-approved neonatal LVAD currently. They have a lot of, just like include this institution, a lot of people work on different kind of very, very small pump for small babies. They always have problems. First thing you have to do thoracotomy to have two access, and you have to widely open the chest. The second thing is you have to have two conduit anastomosis access. One from apex to withdraw blood from LV. Another one you have to go to the ascending aorta. Especially for neonate, ascending aorta anastomosis is always not an easy thing. And even you have that, is sometimes preventing you to close the chest. Those babies leave the chest open, you have a plastic cover. Since if you close the chest, you make this outlet graft may cause the heart or coronary artery compress. What we want to do is the cannula, and I know here you have this concept proved in the adult sheep have apex pump. We tried apex pump before. There's two publications there. The problem is it's very hard. Take a long time to develop those pumps, apex to aorta pump, for relatively longer left heart sensor device. For the neonate, they do not need, it's very hard to have LVAD implant in the neonate for long term because the baby will grow. And the pump you implant is good when you implant, maybe months later, the performance is not good enough, you need to replace it. And then while we develop a simple technology, and then we can do it in simple way. And we have double cannula here, and we withdraw the blood from LV, and then pump back to the aorta. And the insert from apex pass through the aortic valve, deliver to aorta. And our technology is, we tried many neonate sheep. We discouraged it because the very first silver sheep, all the sheep died. We cannot put the cannula in. The neonate sheep is so small. The aortic ascending aorta is so small. It's very hard to get replaced. And then we find out to use a catheter introducer, very long, flexible. And then you even do not need a cut in apex. You only need a puncture by needle. And then you are very easily to have this go through. This thing can monitor the pressure waveform. And then you connect this to the pressure sensor, you can monitor the waveform. You can see here, this catheter is in LV. And then you go further, you can see this catheter, because you can see the diastolic pressure is about 40 something. You can see this catheter is in ascending aorta. And then it's so easy. You have this catheter, go to the LA, you can see the pressure just like CVP. You know it's wrong direction. And then you take it back, and then go there again, and then remove the catheter. We have tried this in 6 sheep, all the sheep, all the cannulation. We can do it rapidly within 1 minute. And you have a catheter inside the aortic valve. The first thing you will worry about is this cause the aortic valve regurgitation. And then we put the sensor here to detect the backflow here. They do increase the backflow a little bit, but it's only very small portion. You cannot diagnose or define as a aortic valve regurgitation. This is our circuit. We have this syndromic pump. Actually, you can use any kind of pump to do so. And you can see the hemodynamic. They can maintain very nice hemodynamic. And then you can see the decrease of diastolic pressure and the diastolic pressure of LV. And you can see all the other hemodynamic is lower range. You cannot see any hemolysis. You can see free hemoglobin is relatively high. There is a half free hemoglobin because of our instrumentation, catheter. You monitor the pressure. Every time when we have catheters, on gas catheter, all the catheter, we see the free hemoglobin increase. And then after 6 hours, you can see the free hemoglobin return to normal level. to the basic level. After 6 hours, you can see the hemoglobin almost the same level as before. We have very, very little blood bleeding through this surgery. And the surgery is through a very small insertion through the left thoracotomy, about 2 to 3 centimeters. It's very easy. And the last thing we have done in past 15 years, we have tried to do something to treat lung cancer. Why? Because the lung cancer is very, very frequent happen in the United States and all other countries, and the mortality and the morbidity increase. And there is no cure, there is no good treatment so far. And when the patient go to the next stage, no matter surgery or chemotherapy, you do not change the expected length, the survival length, lifespan at all. And then we come up use hyperthermia. We increase systemic pressure to 42 degrees Celsius for 2 hours. This technology have helped the ovarian cancer and the colon cancer. And previously they use local hypothermia. However, if this lung cancer spread, you cannot have the whole body homogeneous hypothermia. Previous people use VV-ECMO to increase the temperature, and then you cannot go homogeneous. The brain may not get enough temperature, or somewhere else they don't get temperature. And then we developed Vivo-Venous based on Vivo-Venous ECMO. Use a heat exchanger to develop VVP. Vivo-Venous induced the systemic hypothermia for metastatic lung cancer. In 2004, have phase 1 study, have 10 patients, and the temperature 42 to 42.5 for 2 hours. The median survival increased from 87 days to 440 days, 50 days. And in all of those patients, after VVP, the patient have a serious complication. The patient remains coma for 2 days. And then those worry all the doctors for a long time, because you don't know if the patient will going to wake up or not. And when we relocated to Kentucky, and we figure out what is the reason cause the patient coma, we find that in all the clinical trials, we find the patient's hemodynamic is not stable. It's always need inotropic drug to maintain the normal hemodynamics. And they come here, we find the reason cause of those. Because when you heat the blood, when you heat the prime, you generate bubble, very small bubble. Especially you heat the prime solution from room temperature to 42 and even higher temperature. And then they generate a lot of small bubble, and then they go to the circulation. They have micro bubble in pulmonary circulation. They cause all of those problems. And then we refine our technology, simplify all those things. We produce the primary solution, we solve the problem, make the circulation, make the system very stable and smooth. And now, FDA have approved phase 1 study. And we have tried several patients. This technology may combine with chemotherapy, improve the chemotherapy efficiency. And now it's in second year, and we last year continue our phase 1 clinical trial. And then we're trying to seek further application in the patient. Thank you very much for attention. This is all our research, which is very simple, which is very straightforward. I think everybody understands what I'm trying to do. And there is no fancy technology, and we're just trying to create an easy technology, easy method to help patients. Thank you very much for your attention. Please, any questions?